It's recording.
Yeah, great. Make sure it's pointing at me. Yeah, so last time we actually completed 10.7. I didn't mention that though, so the homework for that is also due on Monday, because you guys didn't even know about it. But in general, how it will go is like once I complete a section, the homework for that section is automatically the next class. And if I forget to say it, that still goes. It was sort of ambiguous whether or not I finished 10.7, which is why
can we still give it in though? Can we still give it in though? Like if you finished it, can we...
If you did, you can hand it in after class. But, yeah. So with that said, so every time you give homework, when homework is due, then I'll answer questions on the homework. So we're just going to jump back into it. Another thing. You guys were supposed to email me like Monday. Some people emailed me Tuesday. Some people emailed me today. Okay, that's fine. At least you emailed me. But I got emails from like 20 people. They're like 36 in the class or something like that. So I mean, some of you just decided to email me for some reason. I don't know why. So here's how we're going to deal with that. Those of you who emailed me by before this class, I will give you 5 extra points on the next quiz. And those of you that didn't email me, I will actually deduct 5 points from the next quiz. Okay? All right, I'm kidding. I'm not going to do that. Okay. No, I'm not going to do that. I'm kidding. But I could have just as easily not have been kidding. Okay? So if I ask you to do something, you do it. My email is actually in the syllabus, on the syllabus. Yeah, it's in the syllabus. It's the second line, Jhevon at Gmail. Pretty much, you email me that.
What do you want in the email?
I explain everything in the syllabus. So at some point you should have read through the syllabus. Here is where I tell you what to email me. So yeah, be sure you do that. Okay. So now let's mention what we did last time. We talked about parameterizing curves. How we can express a using what we call parametric equations. Right, so this is where we describe what each variable is doing separately, right? So we describe x by a function, we describe y by a function, and we describe z by a function, right? Usually we can think of this as something like time. T here is called a parameter, right? That's why they're called parametric equations. And that actually is how we can describe a curve. We can also write RT is equal to these guys. X of t, y of t, z of t. Right? And we also recall that we can do calculus. It's done component-wise. Right, so this is derivatives, integrals, limits. Alright, so if you want to find the limit of a vector function or the derivative of a vector function or the integral of a vector function, all you have to do is just integrate each component separately. Okay? What else did we talk about? Well, we talked about intersecting curves. And this is just, basically we did that by plugging one curve into the other. Right? Because we want to figure out where the x values coincide, where the y values coincide, where the z values coincide. So you figure out what x, y, and z were for one curve, and you plug those expressions into the other curve, and that the resulting expression is the curve of intersection. And that actually covered everything that we needed from 10.7, so now we're going to move on to 10.8, where we discuss arc length. Okay. So your book derives the formula for arc length. You don't really care about the derivation. I'm just going to give you the formula. And you just memorize it and use it all the time. The arc length of given by S of t, that's just a symbol for arc length, that's the usual symbol, is equal to the integral from a to b of the magnitude of the derivative of the vector function. Okay? So, for example, let's say my r of t had two components, x of t, comma y of t. What would the expression for the arc length be between a and b?
Square root of
Right, you have to remember how to find the square root of a vector, right?
yeah.
So we know that if r of t is this, then we
X prime of t squared.
this implies r prime is x prime y prime, right?
Yeah.
Which means that s of t would be equal to the integral from a to b, which these will always be given. How do you find the magnitude of vectors? The square root of each component squared and you add them together, right? So that would be r. And of course, if your r was a three-dimensional vector, then you just add a z prime squared, etc. Right? So it follows the number of dimensions. But basically, the general formula is this one. Right? That is how we compute the arc length of a vector curve. You take the magnitude of the derivative and you integrate it between the points you want to travel, and it will actually tell you the distance that you've traveled between these two points.
Yeah, on the line.
On the curve, yes. Okay, so that is arc length. Let's do a few simple examples. I want to find the length of that curve between t goes from 0 to pi. Okay, so what do we do?
Take the derivative.
Find derivative. What's the derivative?
Negative 2 rad 2 sine t. 2 rad 2 cosine t. 1.
And so if you find the magnitude of r prime, that would equal to what? Square root of this squared, right, which gives you 8 sine squared t plus 8 cosine squared t plus 1 squared. And what is that?
9. 3.
That's 9, right? So this radical of 9, which is 3. Therefore, arc length from a to b would be the integral from 0 to pi of. Don't make this a function. Scratch that out. Because it would be a constant. We take a definite integral, right? And so that would be just the integral of 3 t, which you know is just 3t between 0 and pi, which you know is 3. Okay? So if you want to find the arc length of a randomly given vector curve, you just find the derivative, find the magnitude, integrate that between the limit points, and that actually gives you the length of this curve.
So generally the integration will be the easy part.
Yeah.
Yeah.
I mean, sort of the same. It's not really difficult. So technically, the integration would usually be the harder part, right? Because I mean, I gave you a nice example here, but your function to integrate probably won't always be that nice. I deliberately gave you something that would just give you a constant. It's not always a constant.
Okay.
Right? But you are expected to remember all your integration techniques, right? By parts, substitution, trig substitution, all that. But any questions on that? Well, that's our plan. That's it.
Is this homework also due Monday?
No, I'm not exactly finished. I'm just
No,
telling you.
If you finish it,
If I finish it, it will also be due Monday. Yes. Right? If I finish a section, the homework for that section is due the next class. Okay. We also have a definition. A curve of T is called smooth if so we call something smooth if the derivative is not zero.
Well, zero vector.
Not the zero vector, yes.
Yeah, because.
Right. And do we see why that is? Yeah?
Because the derivative is zero vector.
Almost. It's not just zero, it's the zero vector.
Yeah.
What do you know about a zero vector?
0, 0, 0. It's full zero.
Right, so like in particular, what direction does it point?
Origin. It doesn't have a direction.
It doesn't have a direction, right? So if the derivative is zero, you're like, you don't know what the hell is going on, right? So we say it's not smooth there. And this can happen where you have, for example, a sharp corner, for example. You would have the derivative the vector is zero there if you take the derivative.
So that's why it's sharp.
Right, because if you take it at any other point, of course you can draw a tangent line and you can find the slope. But if you take it at this point right here, well, this is a tangent line, that's a tangent line, this is a tangent line, that's a tangent line. There are tons of tangent lines you can draw going through that single point. It's undefined. You won't know what the hell the curve is doing, and so you end up with things like a sharp corner, which we say is not smooth. It's sharp, it's jagged, right? And sharp corners in general provide a problem, so we just say whenever that problem does not exist, we call it smooth. And we like smooth curves. We're going to do a lot of things with smooth curves, and a lot of the theorems that we're going to use, they will only work for smooth curves, right? Where we actually know what direction we're going in.
By smooth curve, you don't mean the whole curve, but the section that we're working
Just
on.
the section that we're
Okay.
talking on, right? So we are going to be dealing with smooth curves, or what we call piecewise smooth curves, which means the curve has sections that are smooth, that we can break it up
Yeah.
into. But we'll talk a little bit more about that later. But for now, this is what smooth means. Okay. Another thing we want to cover in 10.1. That's just a definition. You should just know that. Right, so smooth curves are nice curves that we can do calculus with because we at least know what is going on there. Yes.
When you say piecewise, we're breaking it up into different pieces by restricting t
Yeah,
value.
like if I have a curve like this.
Yeah, and you would define that by just restricting different t values?
Yeah, I'd say I just consider it here and then consider it here and then consider it here. I would think of this as 1, 2, 3, 4, 5 smooth curves connected. And such a curve I'd call a piecewise smooth curve.
So you wouldn't want to take it from the second one to the third to the fourth one.
No,
because it has that
the sharp corner in the middle is a problem.
Alright, so you would break it up like
Right,
that.
so we can do calculus straight across it because there's a point in the middle where I don't even know what the derivative is doing. Right, so curves like that are troublesome. But
So
we're
it's not
going to learn to
So
deal with
it's
this.
not impossible to do it.
Come again?
So it's not impossible to do it.
It's not impossible, no. And I'll explain why. We actually talk more about that in the next section, in the next 2 sections, right? But that's just a definition that they introduced now. That's what it means to be smooth. And smooth pretty much guarantees that things like this won't happen, right? So if you have a smooth curve, you don't have to worry about sharp corners or undefined derivative or anything like that. Another thing we talk about in 10.8, I don't know if it's important, but it's sort of something you should know. I don't really see it on the finals or anything. It's called reparameterizing. In terms of arc length. Right? So we know about parametrizing in terms of t, right? Where t we usually think of as time, right? So basically I give you a vector curve r of t, right? So if I say the variable t, which considers time. So So sometimes we're modeling our curve in terms of time. So for example, if you tell me what time it is, I can tell you what the location is on our curve, right? So you tell me after some time, right? So this is my curve r of t, and this is where t equals 0 at this time. And by the time, say, t equals 1, I'm over here. So if you tell me what time we're at, I can tell you the location on the curve that we're at, right? But time is not always the only consideration. Sometimes distance is a consideration. For example, I could tell you that, oh, this certain car, we have to refill the gas tank every 30 miles, right? Time is not the answer. It doesn't matter how much time passed before you drive 30 miles. It just matters what distance you cover. So sometimes we're not going to care about the time when the curve is doing something. We're going to care about how far it has traveled. And then I can tell you the location. So in order to do that, we have to change our variable from t to the variable s. So you want to rewrite the function of t in terms of the function of s, and how we're going to do that is we're going to use the equation that I had before. So we're basically going to use that equation.
So inverted.
Particularly. example, I can say my t value is starting at a and it's increasing to some other value. This will be how the variable for arc length is defined, and we can actually find s as a function of t, solve for t in terms of s, and just go back into our function and plug it. So I'm going to do a simple example.
Question?
Yes.
So if you give a question like this, it will be like a word problem. It'll just be directly.
Yeah.
Yeah.
So this is just a straight line, right? And if you tell me a t value, I can plug it in here and tell you the point, right? But what if I tell you, oh, I want the point that we would get after I travel a distance of some amount of feet, right? So I don't want to plug in t values, I want to plug in length values. I can reparametrize, and I will start by doing this. So I know that s is going to be the integral from 0 up to t, right? Because I said t starts from 0, that's the initial, of r prime of u to u. What does r prime look like? So you find the magnitude of that, what do you get?
4, 9, 16.
Alright, so 4 plus 9 plus 16. That gives you what?
29? Oh, 29, sorry.
25. No.
25?
29, yeah, 29.
Right, so this gives you radical 29t. So this implies your t is equal to s over radical 29. Therefore, r, if I rewrite in the expression with the input variable s, it would look like 2s over radical 29, comma 1 minus 3t, which is s over radical 29, comma 5 plus 4 s over radical 29. Right? So here's a curve where if you tell me the distance, I can plug it in here and tell you what point we're at. Right? As opposed to you telling me time and I tell you where we're at. That's called reparameterizing. You're changing the independent variable from time to distance.
So if you had like the units for time is seconds and the unit for distance is like meters, would you be able to convert, like say you had 2 seconds as t, would you be able to convert that into meters?
Well, the units would just go with whatever interpretation you're using. So if you're computing with something else, you'd have it in like meters per second
Okay.
velocity. Right? So your units just follow what you're doing. You don't really have to come, because time and distance, they're two completely different things. You won't really, the units won't coincide. Right? So you don't have to convert it.
But for like a line, it would I mean, if that was a line for velocity or something.
Yeah, so this would be time, which for example is seconds. This would be distance, which for example is meters. I mean, seconds and meters, they don't translate. Okay, and 10.8 is done. That's all for 10.8.
Is that homework due Monday as well?
Yes. Okay. Yeah.
Why did you want us to decrease in T?
Oh, if it's, then you'd put the highest value here and put the T down here.
When would that happen?
If they pretty much ask.
Oh, so there's no reluctance.
Yeah, they're going to describe exactly what they're doing.
Okay, so no reluctance situation.
Yeah, I don't. This is not going to be a trick question. If something like this is asked, they're going to ask you directly. Reparametrize this in terms of. Okay. So that's actually all the Calc 3 we're doing here, and now we're actually going to move on to something different, 13.1. So here's something that we have not seen before, more than likely. And here we're going to talk about vector fields. That's 13.1. So now let's do the definition. Does anyone have any questions so far? Is everyone okay?
I have a question.
Yes.
For the final R that you get, so there's a point that when T equals whatever internal of S, so just plug into this.
Yeah.
425.
They'd say reparametrize in terms of arc length.
Okay.
They would say that in terms of arc length. And then you use that one. Yes.
You said we're skipping curvature. Are we responsible for loading it for the final, or would
No.
not be there?
No, we won't do that at all. Any other questions? Okay, so we're finally in new territory now, so let's start slow. We're going to start with the definition. We're usually going to be dealing with 2 space or 3 space here, so don't really worry about anything bigger than that. That's what a vector field is. It's just a function that at each point we're going to plot a vector, right? So usually, back in pre-calculus when you were plotting functions, you know that if you're drawing on the x-y coordinate, they give you the x and the y coordinate, you just plot a point, right? In this case, we're going to plot a vector instead of a point, right? And the vector field is the function that's going to tell us what vector we should plot. So for example, just describe what this is. A vector field. It's a function, it's a vector function, and I can say it's a function of x, y, right? And it would be given by some function here, fx, y, gx. Right? So we're in R2, which means we're in 2 dimensions, so we have 2 variables and a 2-dimensional vector. And this function tells me what I have to plot. Now, just to make that precise, we're going to do an example. You know what I'm talking about? So I gave you that vector field, and I want you to actually graph it. Graph that vector field. Draw a picture. Okay. So now, I don't expect you to draw a table of values when you're doing things like these, but I'm just going to do it now for clarity's sake. So let's say, for example, I want to draw the vector at the point 1, 0. Right? So I'm at the point 1, comma 0. Right? So I'm here, 1, 0. I'm on the x-axis here. Right? What would the value of f be at that point?
Why is it 1?
It would be the vector 0, comma negative 1, right? I just plug in y equals 0, x equals 1. So at this point, I plot, what does 0, comma negative 1 look like? Just a vector straight down, right?
Yeah.
Of length 1. Right? What if I go to 0, comma 2? Or 2, 0? Well, it'll just be 0, negative 2, right? So it's another vector just a little longer, right? And I continue like that, and I keep plotting vectors. Right? And, yes?
How would you label
1, 2.
Well, you could say 1, 2, 3, but I don't even care about the label. It doesn't matter.
the axis itself?
This is x, this is y.
Oh, so the f of 1.
Yeah. So if you tell me the x coordinate and the y coordinate, I plug it into this function and I get a vector, and I just draw that vector at the point. Right? So now, if I'm on the line, let's say I'm at a level where the y equals 1, what would that look like?
And x equals 0.
It would be 1, negative 1.
Like here, if I'm at 1, comma 1.
Okay. So 1 negative
1, negative 1.
Right, so if I'm at 1, comma 1, I would just get 1, negative 1, right? Which looks like what? A little to the right, but down, right? So it's like that, right? And all these are going to look like that, right? And if you keep plotting, so eventually you're just going to plot enough to get a pattern going. If you plot a bunch of points here, you're going to realize that this is the pattern you're getting.
So we'll need to actually graph it.
It's actually just a swirl, right? So whirlwind. If you plot enough points, you'd realize that that's the pattern you're getting.
So we'll actually need to graph some
It's a
vectors.
sketch. Like you're never going to use graph paper for it. That's just like a sketch. You know, like if someone says graphics squirt, you don't pull out a graph sheet and it's a sketch. You just have to have an idea of what's going on. But that's how a vector field works. So it's just a function. It's given as a vector function, and how you find out what it looks like is you plug in each coordinate into the function and you find all the vectors, and then you plot the vectors. And you only plot enough so that you get an idea of what's going on. Usually, after you plot a few of them, you sort of realize what's going on. So you'd realize that if you're applying here, everyone's going in that direction. If you're applying here, everyone's going that way. If you're applying here, everyone's going that way, then this way, then this way. And you're just like, oh, it's just going around. So this vector field actually looks like just a whirlpool or something like that. So for example, if we're plotting a vector field to describe the flow of a fluid, and water going down a drain might look like that when you're looking from above, right? So that would be a model for water going down the drain, for example. And if we plot a z coordinate being negative, we know that it's going down. So you can see, oh, it's swirling this way, and at the same time it's going down. And so that vector field would describe a very basic model of.
Could you have one of the x or y functions be like a square root? In which you
Yeah,
have two answers?
any function, right? This is f of x, y, g of x, y. These can be anything at all.
But if you had a square root, you would have two answers. So how would you treat that?
Square roots don't have two answers.
What-
Like
what
if I
plus or
put the
minus?
square root, if I put square root of 2, I just mean the positive square root of 2. We're
What
talking
if you
about
had like square root of x?
square root of x.
Yeah, so then
Then that means that your vector field would only exist where x is positive.
Only if x is positive?
Yeah, because you can't take the square root of a negative. Not in real.
But the answer for it, it's going to be plus or minus whatever number.
No, it will just be the positive. Alright, that means principal square root. There's a difference. If I say the plus or minus comes when the square root comes from actually solving the solution. Right, like if I had radical x equals 4, like x squared equals 4. Then if I solve for that and say x equals radical 4, here I have to put the plus or minus, right? Not because the radical itself is a plus or minus, but because the answer over here could be a plus or minus, and I still get the positive. Right, so it's a way you look at it. In calculus, when we write square root, just mean the principal, the positive one. If I mean the negative one, I put the negative in front. Yeah. But in general, these functions can be anything. You just plot whatever they do. Right? So this function, for example, gives you a swirl, and that is called a vector. Right, so a vector field is sort of what you think of it is, right? So just a field of vectors that describes the motion of something. Could be an electric field, a fluid field, wind flow, anything.
Heat transfer?
Right? Heat transfer, whatever, right? So where your direction and magnitude have some interpretation that you understand, right? And so your mathematical model would look like you just plot a vector function, right, to describe that field. An important field for us will be gradient field. Okay. So this is so it's the familiar del f from Calc 3. So in this case, del f of x, y would be just the partial derivative, right? Right? So if I give you a three-dimensional function, scalar function, it's just partial with respect to x, then the partial with respect to y, then the partial with respect to z. Right? So this is going to be a very special field that is called a gradient field, right? It's the field of partial derivatives for the components. It inspires the following definition. A field F is called conservative if f is equal to the gradient field of some scalar function. So if the vector field you realize is actually the gradient field of some other function, you call it a conservative vector field. The name is very suggestive.
But aren't all gradient vector fields?
No, you got curl.
Oh yeah.
Oh, yeah?
Yeah. But aren't all gradients gonna be vector fields? Yeah.
Yeah, every gradient field is a vector.
Yeah. So
Yeah, but not every vector field is a gradient field.
yeah.
Right? There are vector fields for which there is no function you can come up with that if you take a gradient you'll get it. Right? And you'll see problems like that in your homework. But whenever this does happen, it's called conservative, right? And that's just a definition that they tell you now. We're actually going to explore that a lot later. That's going to be a really important concept. So just for now, just observe that definition. Okay? In this case, f is called a potential function. Now, gradient fields are going to be really important. A lot of our theorems that we're going to have later on are going to be dealing with gradient fields because conservative vector fields have a lot of properties, and we're going to be able to use some analogous forms of the fundamental theorem of calculus on these particular kinds of fields. So they're going to be important, and that finishes 13.1.
Oh, cool.
So homework for that is also due. These sections are short, don't worry about it. The next section is going to be a lot longer. I think we will stop there. Any questions? Yes.
For a vector field, could you have like say you had a baseball that's being hit, that it's already hit, so as it travels through space, it carries a specific momentum in different directions. Is that a vector field?
In a limited way. I wonder you describe as a vector field. It's probably more like a vector curve. The ball doesn't really occupy.
And when you say scalar function, what exactly do you mean by that?
Just a function that's not a vector. I gave you an example. So for example, if I say f of xy equals 4x squared